Let's chit chat about kind of what some of your answers should be, all right? So, again, all we're kind of showing is like, hey, let's just make a sketch. Doesn't have to be exact, but at least it's going to give you an idea of where you should end up, okay? So let's say, for example, you have number 6, okay, because that's one of the more difficult ones. So on number 6, and again, all I'm doing is just making a sketch, okay, just so we have an idea of where we should end up. So you start off, here's your x and y coordinate system, tip to tail method. You got vector B, boom, straight up, 3 centimeters. So there's B. Make sure every vector has an arrow on it so I know which direction this thing is pointing, okay? You don't have to write out the 3 centimeters at 90 degrees, but at least show me the arrow, okay? Then you got C, and again, when you draw this, all vector, the end of vector B, all that does is show you where to draw the next 120-degree angle, okay? That's all it does. It tells you, hey, this is where the next vector is going to start. So then, you got C coming up here like this. Now, the tricky one on this one is D. And D tends to give kids fits because it requires a little bit of thought. So that's 250 degrees. So you've got to end up down here somewhere because, again, this is always defined from that positive x-axis of 0 degrees. So here's 0 degrees. You're going to come around here like this, put that protractor like this, find that 70-degree mark, and draw it coming down here like this. Okay? Now, just a sketch. That's all this is. But it at least tells me an idea of where I'm going to end up. So when I draw that resultant vector, coming out here like that, and that's the heart and soul of this. The heart and soul of this is that resultant. Now, Charles, ballpark, what's that angle going to be for that resultant? Estimate.
Close to 180.
Yeah, more or less than 180.
Less.
Less. Based upon this diagram, that angle is going to be a little bit less than 180. So, and that's what it should be. That answer should be around 170 degrees. So, by making just a sketch, hey, I get an idea of what should be happening. Okay? So, both of those angles on 6 and 7, those angles should both be around 170 degrees. Okay? It's an ish, but it's going to be somewhere around in there. Okay? Cool with that. Any questions on 2 through 7?
No, you do over 7.
Yeah. So it's the same idea. You're just going to, I'll just sketch it out. So you're going to have A, B, C, D, and E. So then that resultant is going to go from here out like that. So that's what it should look like. That help?
Yeah.
Fantastic. Okay. Now, let's talk about number 8. So a lot of times, the cool thing about a problem like number 8 is that it's going to show you the times when you need to set up like a scale. So if you look on number 8, Bob travels 3.8 kilometers. Well, it isn't realistic to draw a vector 3.8 kilometers long. 3.8 kilometers is like 2 miles, okay? I really don't want to draw a piece of paper where I'm going to draw a vector 2 miles long. Not realistic. So a lot of times, we need to set up a scale. So what I would recommend is you hey, I'm just gonna let 1 centimeter equal 1 kilometer. Okay? It's a nice 1-to-1 ratio. You could let 2 centimeters equal a kilometer, yes.
You need that like conversion on the graph, or do you prefer it on like the paper?
What do you mean?
Like where do you need to see that? Like,
On
you
the
want it
graph itself would be
On
cool.
the graph itself, okay.
Yeah. Because that way I can look and see that all at one place.
Okay.
Okay, and again, we're just gonna make a sketch, okay? So you've got 3.8 kilometers at 45 degrees. And then he's gonna turn and go straight south at 270 degrees, 5 kilometers. And then he's gonna go over here like this at 225 degrees, and that's 6.5 kilometers. And here is that result. Okay. So here's the fundamental difference in this problem. And this is also going to play out with forces, which is what we're really going to get into tomorrow. So every force problem is relevant to force vectors. And every force problem can only go one of two ways. There are only two things I can do with any force problem. I can either have the object move at a constant velocity, or I can make the object accelerate because of the forces. That's it. Those are the only two things I can do. I can either make the rocket accelerate, or I can make the rocket cruise at a constant velocity. Nothing else I can do. So the question being is that how does that look in terms of forces? So here's the story. If you take any number of forces, in this case there's 3 of them, if you draw all the forces acting on a system and you do not end up back at the origin, that means the object is going to accelerate because the forces aren't balanced, okay? So if I tell you, hey, a rocket ship is launched and it accelerates upward at 4 meters per second squared, right away, you know when you draw all the vectors acting on that rocket, they're not going to end up back at the origin, and you're going to draw a resultant, okay? Same thing is true with your car. When you're driving to school, assuming that you're driving in a straight line, your car can only have one of two things happening to your car. Your car is either moving at a constant velocity or your car is accelerating. That's it. Nothing in between. So either all the forces are balanced or the forces are imbalanced. So let me give you an example. You're driving along. You know you need to turn into, let's say, Scooter's Coffee. Let's say you're a scooter girl. Okay? Hypothetically. There might be someone in the room that's a scooter girl. I don't know. And you need to turn, right? What?
I don't know why she's laughing.
I don't know either.
Wait.
So, you hit the brakes. Do you accelerate when you hit the brakes? Yes. So there's an imbalanced force created by the brakes. Now, you're leaving scooters, and you need to speed up. What are you going to do? You're going to hit the gas pedal, right? You're going to begin to accelerate. You're going to create an imbalanced force. Now, later on, I'm going to drive at 40 miles per hour. And I'm going to maintain that speed of constant 40 miles per hour. All the forces are going to add up equal to 0, and you're not going to accelerate. So, everybody says, physics is hard. Forces problems are only one of two things. Either the forces are not balanced and you accelerate, or they are balanced and you have constant velocity. That's it. Now, if I do make the car accelerate, what are the only two things I can make it accelerate? What's the only two things I can make it do? Speed up, slow down. Literally, that's every force problem that exists in the world. So, in this situation, instead of distances, let's say these are forces that are acting on your car. If you draw those and you end up here, the resultant, and this is going to be the difference, the resultant here is going to be measured from this 0 degree angle around like this. Now, again, just a sketch. Just a sketch. Here's 270 degrees. Okay? Just a sketch. Based upon the sketch, what is my angle from, and this is going to be the whole thing, the whole key to this. This is the search party's angle. The search party's angle, based upon a crude sketch, has to be between what and what? 90, between 180 and 270. Probably closer to 270, just on a simple sketch. Okay? Again, if this was forces acting on a system, this would be the direction that it's going to accelerate. Okay? Now, if you're Bob wants to go back to camp. If you're Bob, I'm going to measure this angle. So Bob's angle is going to start here and come up like this. Okay? So this angle is measured from this x-axis and around like this. This one is starting here, and it's going to point in that direction. So if all the forces add up, when you draw that vector back up there, you're going to have constant velocity. So here's a simple example. So on Earth, this apple weighs 1 Newton. Okay? We'll get into forces tomorrow. Boom, it says right there, 1 Newton. This is what it weighs, 1 Newton. Is the apple accelerating?
Yeah, no.
No, it's not. Has a constant velocity of 0. All the forces at this point do what? Add up to 0. So what's happening with the apple is that I've got a gravitational force acting down of 1 Newton, and I'm providing an upward force of 1 Newton. It adds up to 0. I don't accelerate. I let go of the apple. What's it going to do? It's going to begin to accelerate. Because at that point, what do the forces not add up to? 0. What's the only force left acting on it when I drop it? That's the direction of my acceleration. I push the apple along at a constant velocity. Do all the forces add up to equal to 0? Yes. There's forces that just add up to equal to 0. Now if I push it and I stop pushing it, what does it do?
It stops.
It stops because there's an imbalanced force of friction that makes it slow down. So that's what I'm telling you. Every force problem that you're going to do starting tomorrow, either you draw the vectors and you end up back at the origin, you're at constant velocity. You draw the vectors, you don't end up back at the origin, you accelerate. And then once you accelerate, what are your only 2 options? Speed up or slow down. That's forces. You understand that, you have 80% of forces done. Okay? That's it. That's 80% of forces. Now, when you answer that last question on 8, it says, what is the relationship between the direction and magnitude of the search party's path and Bob's path? So help me. If your answer involves the word different, I'm going to flip out. Okay? Do not tell me, oh, the angles are different. Horrible. Bad. Bad. I have no idea what different means.
Specify why there is a difference.
Well, or specify what the value of the difference is. Okay? Just do not say the angles are different or the angle changes. Okay? This is not a political campaign. All right? Give me something more than that. Cool with those? Got it. Good. Great. Okay. So, again, understand why I had you do this. And this is also why we didn't do a lot of them. It's like, okay, hey, Burkamp, we got it figured out. Here's the process. So now we're going to take that information and roll that into trig functions. Okay? So, let's start with the big 3 trig functions. Jacob, what does the sine of theta equal? What over what?
Opposite over hypotenuse.
Beautiful. Woo! Woo! Scooter,
Oh, no.
what does cosine equal?
Adjacent over hypotenuse.
That's, I'm gonna tell you right straight up. That's what I'm gonna call you now. Scooter. Scooter and Sid. So, Mr. Hannah, what does a tangent equal?
Opposite, no? Hypotenuse.
No? Opposite over adjacent, right? And then you got the Pythagorean theorem, which is beautiful. No, no, no.
Know that?
This is all we're gonna do. Sine, cosine, tangent. Now, these are cool. Fundamentally changed how we understood the world. But what's the only type of triangle that these work on?
Right.
Right angles, okay? They only work with right triangles. So in case you haven't noticed, a lot of the vectors that we're gonna deal with
Aren't gonna be.
aren't at right angles to each other. So we need to be able to handle how that plays out.
Okay, back to the wall.
So, here's what we're gonna do. We're kind of working through this together. So down there on number 9, we're gonna use the same vectors that you drew up above, okay? The exact same vectors. So, I'm gonna draw this out. I'm gonna say, okay, here's vector A, 5 centimeters at 0 degrees, okay? So, here's the story. Connor S is going to start here, okay? I need to tell Thatcher how to get to where Connor is going to end up. So, here's the story. One option is that I can say, hey, Connor's out here. Thatcher, you need to walk 5 centimeters at 0 degrees. Boom, he's got it, okay? 5 centimeters at 0 degrees is cool. Now, the other way that we can do this is with a Cartesian system of x and y coordinates. So, here's my question. If I told Thatcher to go to the point 5 centimeters and 0 centimeters, is he going to end up at the exact same point he would if he walked 5 centimeters at 0 degrees? Yes. Okay? He would. He'd end up at the exact same point. So, this is a simple example, but here's what I want you to see. If I give the x and y coordinates, or if I give a single vector with an angle, I end up at the same point. Okay? X and y, boom, there you go. So, right here on vector A, where it says the x component and the y component of 5 centimeters at 0 degrees, is the easiest point you are ever going to get in this class. What's the x component of a 5 centimeter vector at 0 degrees?
5 centimeters.
5 centimeters. What's the y component?
0 centimeters.
Easiest point you ever get in this class, right there. Okay, that's it. 5 centimeters, 0. Now, you got vector B, 3 centimeters at 90. I've always found, from my learning perspective, that I'm a very visual person. I always make a sketch of these problems because I like to see what's going on. I like to see how things are oriented. So I got 3 centimeters at 0 degrees. Oh, excuse me, at 90 degrees. So Luke, what's the x component of a 3 centimeter vector at 90 degrees?
0.
Beautiful. What's the y component?
3.
Positive 3. Okay? So here's the story. I could tell Chloe to do one of 2 things. I could tell Chloe to move 3 centimeters at 0 degree, at 90 degrees, or I could tell her to walk to the coordinate 0, 3. Will she end up at the same position both times? Yes, they're both equally valid descriptions of how you get to that. This is where it gets sketchy, though. It's not bad. We can handle it. So C is 4 centimeters at 120. Man, this is tough
You're telling me.
at 120. Okay? This is tough. Why? It's not a right triangle. Okay? It's not on the X or Y axis. Okay? This is not cool. But before we tackle that, we'll get to that. Let's say that that had been 4 centimeters at, say, 40 degrees. Okay? Let's just back up a little bit. Let's tackle a simpler one first. So, what I want to do is called deconstructing the vector. Okay? That was loud.
I'm sorry.
No, you're not.
No, you're not. Let's be honest. No, you're not. Okay. Nice speech, by the way, this morning. Nice speech at the pepper.
I didn't
Yeah,
know I was
it was
supposed to
tough.
do anything, bro. Nobody told me anything.
6:30 or something.
It just put you on the spot.
Okay.
and
Anyway, I was like, oh, there's
He
actually.
wanted to make a grand appearance.
I get it. I get it. Okay. So here's the story. What I want to do, so Connor M is here. One situation, we told Connor M to travel 4 centimeters at 40 degrees and he got to this point. I'm going to tell Connor A how to get to that same point using an X and Y coordinate system. Okay? So this is why this is called deconstructing the vector. I need to take that vector and find the X and Y components. Because what you all did yesterday is that you had the X and Y components and then you drew the resultant. This one I'm going to give you the resultant and then you work backwards and you find the X and Y components. Okay? Now, you got a Y component and you've got an X component. The 4 centimeters represents the hypotenuse and I know the angle. So Connor S, am I going to use sine, cosine, or tangent, knowing the hypotenuse to find that Y component? So the sine of theta is going to equal the side opposite, which is your divided by the vector, and the vector is always going to be the hypotenuse. So Connor S, how am I going to get Y by itself?
Multiply the vector by sine.
Beautiful. Okay? Now, if I use sine to find the side opposite, what do you think I'm going to use to find the side adjacent? Cosine, right? So x is going to equal the cosine of the angle times the vector. Okay? Now, let me show you the old way how this used to be done when I was in school. So, when I was in school, you had the sine of 40 degrees times 4 centimeters. Okay? Is that door open?
Yep.
Oh, shit. So, no, this was not my high school physics book. Okay? I'm not just, that wasn't that funny, Scooter.
Sorry.
Okay? So,
That was funny.
that was fun. Okay, so this book was published in 1902. Okay? 122 years ago. So I said, I'm not that old. But here's the cool thing about this, is if you come back here and you look at the index and all the key words, this is from 1902, physics book. If you come back in here and you go to like the section that has E's, all the E words, you can't find the word electron. If you go and try and find the word proton, neutron, none of those words exist within a physics book from 1902. Why?
Because that's chemistry.
Hadn't been discovered.
Yeah, we hadn't found it yet. Okay? At that point, we thought atoms were the John Dalton description, that atoms were indivisible. 22 years ago, we did not know the structure of matter. We thought atoms were indivisible, okay? Now, you're going, it's kind of cool, but how is this relevant to trig functions? So in the back of any advanced math or science book, you would have this, okay?
Oh,
So this is the table of natural sines and tangents. And I always laughed with like, table of natural sines. Is there like a table of like unnatural sines? Like, come on, what does unnatural look like? So, at the time, and I was in high school in the early 1980s, we did have calculators, but calculators would not handle trig functions. Okay, like there was no sine, cosine, tangent. You would add, subtract, multiply, and divide, but they hadn't developed the computing power to handle trig functions. Now, let me give you some perspective on how calculators have changed in my lifetime. So I grew up in Cheney, lived there through 6th grade. In the early 1970s, the science department at Cheney High School paid $400. Now, to give you some perspective on $400.
That's like 10,000 right now, right?
Oh, for $100, you could buy a good used pickup for $100.
Oh, wow.
Okay? You could buy a good used pickup for $100. Okay? They paid $400 for one calculator. That would add, subtract, multiply, and divide. It was a 4-function calculator. Paid $400 for it. Okay? Science departments from around the area would go to Cheney High School just to see their calculator. That would add, subtract, multiply, and divide. Because that was the coolest thing people would ever see.
Did you have color?
Huh?
Did you have colors or no? Did you see there's colors?
What do you mean?
Like, was it all black and white? Was
Black
it
and white.
So you have colors.
when?
Like in pictures?
In anything.
Okay, color picture. You can find
Yes.
color
We just couldn't. And color film really came into being in like the late 1960s.
Oh.
Okay? So, yeah, we just didn't have the capacity to really capture that.
Oh.
Yeah. There was brilliant sunsets and everything else. So, yeah. Okay.
Serious question.
It's a serious question. I gave a serious answer.
Everybody laughing.
Okay. Green was not an invention of 1970. Okay? Green's been around a while. Okay? All right. Blue skies, we've had it. Okay? So, here's the story. So, when I was doing this, and again, this is in the 1980s, what you would do, how I would do this problem, I would go to this table, and I would find 40 degrees, okay? And I would look up the numeric value of the sine of 40. So somebody take your calculator, which does do trig functions. Make sure that you are not in radian mode. And punch in, all I want is the sine of 40. Okay? 0.643? Okay, so that's what I would do. I would look up the sine of 40. I would find 40 degrees and I would go across, and that's 0.643. Okay? So then I would take 0.643 times 4. Now, calculators can handle that. Now, my high school chemistry and physics teacher, a bit of a jerk, Jim Tyner, rest his soul, would not let us use calculators on the test. Okay? We'd use it on homework, we'd use it on labs, but we could not use calculators on the test. So this is the old slide rule. So if I were doing this problem, and back in the day I knew how to use the slide rule, that has since sailed, but I would take 6.43, because you couldn't find 0.643 on the slide rule, but you could find 6.43. So I'd take 6.43 times 4, you'd line them up, and then you'd slide this, and that's how you would get your answer. So in the old days, this is how you did trig functions. Now, another reference that we had and this is well before the internet,
My God.
was this book, okay, which is the Handbook of Chemistry and Physics. This is from 1947. Every good chemistry and physics lab that existed had this book. This was like the science Bible. So, yeah, this is a thick book, but it's cool though. So like you would have, like, I just opened it up.
Yeah.
Like, here's the physical constants of organic compounds. So we would have the name, the synonym, or the synonyms before the synonym, the chemical formula, and the molecular weight. You might go to the next section. Viscosity of alcohol water mixtures. I mean, literally, this had the most random things that existed. But always within this book, there was a table of sine, cosine, tangents. But they all stopped at 90 degrees. Okay? They all stopped at 90. So if you had something more than 90, you had to do something different, which is what we'll get to. So here's what I want you to see at this point. X is going to be the cosine times the vector. Y is going to be the sine times the vector. Okay? Now, back to this story of 120, now that we have the backstory. Okay? When I would do this problem, I couldn't look up 120 degrees. Did not exist in the table. 120 was not there. But I can do this.
The inverse.
Well, what's that angle going to be?
60.
Wait.
60 degrees. I could look up 60 degrees. Okay? Now, personally, from a visual standpoint, it's easier for me to see that if I use that 60 again, it's just me, it's old school. For me, sine and cosine of 60 degrees in terms of opposite and adjacent makes more sense than trying to find the opposite and adjacent sides of 120. Okay, because you think, oh, the side opposite of 120. Oh, that should be somewhere up here, which doesn't make any sense either. So, personally, I would work off that 60. Your calculators can handle the 120, but let's think this through though. When you do this, what's the sign of that x component going to be? Positive or negative? Negative. What about your y component? Positive. So here's what I want you all to do. Make sure that you can do this. So we're going to use trig functions to find these x and y components. So somebody to get that x component, take the cosine, you can either use 60 or 120, times 4. What'd you get? Exactly? Centimeters. Okay, cool. And did your calculator tell you it was negative value?
Yes.
Okay.
Use 120.
Now, on your y component, you're going to take the sine of 120, or again, you could use 60, times 4. What'd you get there? 3.464. 3.46 centimeters. So, here's the bigger picture, okay? There's two ways I could tell Connor A to get to this point. I could say, Connor, you go 120 degrees and you walk 4 centimeters. He's going to get to this point. Or I could go to Connor M and go, hey, Connor M, you go -2 and then you go up to 3.46. In both situations, are you going to end up at the same point? Yes. But this is called deconstructing the vectors because you find the x and y components of them. So, right quick, fill in number 9 and then we'll move to the next point. So, Andrew, stop right here for a second.